All right. Welcome everybody to this second spring 2024 seminar, and I think it's going to be a hit. So we have with us Igor Halperin, and he was named Buy-Side Quant of the Year in 2022. He has a financial career that involves stints at Bloomberg, JP Morgan, and now Fidelity Investments. And he's also a well-published academic author with books on machine learning before anyone was doing machine learning, and he taught at NYU Tandon. So basically, he's got a background in physics, which is really interesting, and I've always been a fan of econophysics. That I was reading 20 years ago, and with literature by people like Jean-Philippe Bouchot and Doyne Farmer. And, thinking of the order book as this system with lots of particles that interact with each other, that's something that has inspired a lot of my research. And I think it's a great way to look at finance. But as many of you know, a lot of financial engineering is built on diffusion models, which is originally a physics concept. So I personally quit physics before quantum physics. So that's why I guess today I'm really excited to hear this talk, which is called Schrödinger Control Optimal Planning for Goal-Based Wealth Management. And there's a link to the paper that you'll find in the chat. And if you have any questions, please leave them in the Q&A. So I might keep them to the end, but I might also ask them in the middle of the talk. So right, Igor, it's all you. You can take it away.
Well, thank you so much, Sasha. It was probably the best introduction of my presentation that I ever heard, and that's exactly, you started exactly at the right point. This is indeed like econophysics is what brought me about 24 years ago now to finance. I just decided that the next century I will start in a new profession. That was the story in short. And around that time, indeed, econophysics papers and these papers by Jean-Philippe Bouchot and Eugene Stanley came, and this is what sparked my interest. So what I'm going to present today is actually the first work in everything that I did so far, where all three topics of my previous and current research converged into one, and which are actually finance is one of them, another one is optimal control, and the third one is physics, but physics comes here as a tool only. All right. And then there's this fancy name, and I will try to what is it? How do I, sorry, how do I move it here? Maybe like this. Oh, yes. All right. So this is the outline of my presentation. So what we'll very modestly claim here is that we address $1 million problem, which is routinely solved by millions of working individuals, both in the US and worldwide. And more specifically, what we'll be talking about is what is called goal-based wealth management and optimal retirement planning. So what I'm going to do in this talk, let me, sorry, trying to move a little bit. Yes, this one. One sec. Just trying to move this thing here. Right. This is the plan. So first, I will solve a particular model for a goal-based wealth management by reducing it to a control version of a very classical problem from quantum mechanics, and then I will solve the latter. So this is the technical part, which may or may not be of interest for a majority of our audience. But for those of you who do not have background or don't know much about partial differential equations, so just as a way of preview, I would like to suggest that maybe, like, when in the middle of this presentation, we'll get into more technical points where you might find yourself a bit lost. So first of all, there's a fuller paper with all technical details, which is available. But second of all, maybe what it would be more important is conclusions from this and further questions which come as a result of this analysis. And this is where I will try to make a connection, which I think is very interesting and somehow was not, at least I didn't see this discussed before. What I mean is the connection between this goal-based wealth management and satisficing decision-making theory of Herbert Simon. And then I will introduce something what I call maybe, well, there've been some debates whether the name is appropriate or not. You will decide, but at least the meaning will be clear. I call it efficient frontiers as some sort of, degenerate continuous solutions of this problem. And I will try to explain why these solutions are interesting and why they bring further questions. So, and this will be the topic of this last item in my plan, where I will talk about problems with the traditional reinforcement learning or optimization-based methods for goal-based wealth management. And here, if you wish, is poetic summary of this talk. All right. Still understand that they should. Let me maybe stick to this. So these are here in this slide. I just collected few names of researchers which somehow whose work is somehow related to the topic of this talk. If you don't recognize some of all of them, they will reappear shortly. But this is essentially the sequence of this presentation: wealth management to satisficing control to physics, which is scattered between this. All right, so let me talk first about evolution of wealth management modeling. And of course, as everyone in finance knows, modern financial theory and also modern financial practice started with celebrated Markowitz portfolio theory, which later, more specifically in applications of, so that was the most groundbreaking work. And the second very important work is associated with the name of Robert Merton, who came up with the first paper, I think dated even before Black-Scholes, 71, as far as I recall, about utility-based financial planning. So what he addressed is what is now called Merton consumption problem. He addressed the problem of retirees post-retirement, how they optimally spend whatever they have. Right. The third key entry here is the whole approach of goal-based wealth management, this GBWM abbreviation, and optimal retirement planning. I put here the photograph of Professor Sanjeev Das, whom I know personally, as one of the pioneers of this approach. Maybe not their first paper, but a few of important papers in this direction are written by Sanjeev. And finally, which is not the part of this, usually not the part of this links or stream of work, I will try towards the end of my conversation connect it to another Nobel Prize winning work by Herbert Simon, and more specifically related to his satisficing decision-making theory. All right, but first let me talk a little bit why what I present today here is it can be thought as some sort of a non-standard problem for reinforcement learning. So first, let me start why. So what components here are standard components? The standard components are that if we think of optimal wealth management, then it's obviously a problem of control, right? Where your control is how much money you deposit to your retirement plan. That's your decision variables, right? And this control goes over multiple time steps. So it's a sequential control, sequential multi-step decision making. And obviously, because it deals with the future, it involves some elements of planning. Like, so you have to plan and forecast into the future. All these are very conventional elements of most of formulations for optimal control, not only in finance, also beyond, right? And also all these elements that I outlined so far are the same actually as in this famous Merton optimal consumption problem, the paper that I just mentioned before. Right. But in what I'm going to do, there are three major differences between my approach and this standard approaches. So first the first difference is that I would not use any utility function or any consumption process. The Merton approach deals with utility of consumption. And instead of that, we switch to the formulation of goal-based wealth management by Sanjeev Das, and we have a more specific objective function, which I'll present to you shortly. The second, which is more important, even more important, we actually do not do optimization. And this is the key difference between what I do and the standard approach. Because the Merton approach, Merton optimal consumption problem, it uses dynamic programming approach, and dynamic programming approach amounts at the end to some sort of optimization. You optimize the cumulative reward. We do not do optimization, and this is critical observation. I'll come back to this later. And the final difference is that the setting of my paper corresponds to open loop optimal control rather than to adaptive control, which is done in both in Merton's approach and in all reinforcement learning based approaches. Maybe here I should explain what I mean. So, so both dynamic programming and reinforcement learning in its standard formulation, they assume that you adjust your optimal policy to the environment at each time step. So, which means that if you work in continuous time, then you do it continuously, right? And that's why it's called adaptive control, because it adapts continuously to changes of the environment. Now, this is not always necessary, and actually, in many cases, it makes things unnecessarily complex. And also, as I said, it does not correspond to realities of life. So in our particular application of wealth management, the way it works, people who have retirement plans, they talk to their advisors once a year, something like that, right? So they set policy. In these terms, they set policy once a year, and then they follow this policy. And then a year later, they come back to this, and if necessary, they revisit the assumptions, right? So this is called, like, this is the setting of the approach, which is called model predictive control, right? And it's different from adaptive control settings, which are done in reinforcement learning. Exactly in this sense, you do not change what you do, your policy at each time step. So that will be my setting. If there are no questions, then so far, then I can go to the little math here. So, so the math is shown here, and actually it's pretty simple. So what we say is that we have a financial planner, which is a retiree in our case, and their portfolio is made of cash, which we call B sub T, and stock S sub T. And the equity ratio in this portfolio is called omega, right? And now we assume that the portfolio is managed by a fiduciary, which means that it's a job of fiduciary to maintain optimality in the portfolio. So we leave this part aside, right? So here I only focus on the problem of a retiree, which is how much money to put in their retirement portfolio, right? So that's what everyone like almost everyone in the United States who works and has 401k does, right? You decide how much money you put aside, not anything about reallocation, and that's my setting here. All right, so we assume that at each time step the planner contributes amount C sub t times delta t in terms of after-tax money to the portfolio. And then because the portfolio has to maintain this fixed equity ratio, right? Then this condition triggers some trades in the portfolio, and these trades amounts to adjustment of both the cash account, which we call B. So immediate change of B right after the injection of money. When the previous value was this, the new value becomes this, which is the adjustment, right? And respectively, you also adjust the stock position, right? So if you sum now, this is the new value of the stock position, the new value of the cash position. If you sum them up, then you will see that the change of your portfolio is exactly equal to this guy, right? Minus the transaction cost, all right? Now, and we visualize the dynamics in this form. Right after in each time step, we have cash injection to the portfolio, which triggers adjustment between cash and equity component in the portfolio. And then in the remaining of this time period, this portfolio grows with some random return, right? And this random return, as usually, is given by the combination of the expected value, which we call R hat, and random value, which is proportional to the standard Gaussian random variable. So nothing fancy here. We have some parameters which correspond to the volatility and expected return of your portfolio. Obviously, I don't show this here, but obviously both these guys depend on your equity ratio, right? But it's simple to compute, right? So if you have like standard assumption, nothing fancy again here at this stage, right? So I don't assume any stochastic volatility, like my volatility assumptions are just this, very simple, normal returns, right? The game will not be around volatility. All right. And these guys, like, they can simply be related with the market return and market volatility corrected by this equity ratio. So now if we take these dynamics and take the continuous time limit, then we can express the dynamics in terms of the stochastic differential equation for the portfolio. So portfolio is the sum of the stock and cash defined here, and then the stochastic differential equation for the portfolio will look like that. All right, so now what's interesting in this equation is a few things, right? So first, this U is just the, where it's defined here, yes. U is just the rescaled corrected by the transaction cost, but it's essentially, you can think of this as your cash flow, right? So U here is your control. That's how much you contribute each month to your retirement plan, right? And you see that this U is not multiplied by P. So if you cross it out, then you will immediately recognize in this equation simply the equation of the geometric Brownian motion model, right? So it's the same equation that would go into Black-Scholes model, for example, right? However, here we don't have that, right? Because of this term, this is our control, and you see that this control is not proportional to portfolio value, which is critical. If it was, then everything would simplify, and nothing of what I'm going to present would be needed ever, right? But that's the equation, right? And by the way, that's the same equation, obviously, that Merton had in his optimal consumption problem. That's the dynamic, right? It looks super simple. Nevertheless, it's so far from simple due to this term. All right, so
quick question, Igor. Should the DW term also be scaled by this, by the control, or
no. In this setting, no. In this setting, like if you follow this simple math, then control only affects the drift term, not the diffusion term. So the diffusion term is standard, completely standard.
Okay.
It's normal volatility, right? So it's a volatility times the state variable. P is my state variable, right? So this is the same as geometric Brownian motion, this guy.
Yeah. Okay, so if your equity ratio goes from 0 to 1.
Yes. I'm sorry. Yes. Yes. You are right. It's not market volatility. It's this volatility. Yes. So it's impacted by your equity ratio.
Okay.
If this is what you meant. Yeah. It's my fault. Yes, indeed. You're right. What I meant is that this is simple adjustment. This is like my equity ratio is a parameter. It's not my control. Right. So this thing is like rescaling of volatility. The whole game is around this term. Okay. More specifically, due to this is my control. I will momentarily extend it. So this is like UT. That's the critical part here, right? So UT is the contribution each month into my plan.
Yeah. So let's say you make $1,000 this month and your W is half, you're putting 500 in a fully invested portfolio or
yes.
Okay. Yeah.
Right. Okay. All right. So this is my stochastic differential equation, and now we have many ways to work with that. We can simulate it, but I don't want to do simulation. I want to rely on probabilistic methods. So, and I'll do few transformations to this equation. So first is that so here I introduced my U, and U, if you see here, U is essentially like your cash flow, which was defined here, corrected by transaction cost. All right, and this is how much you would contribute each month if you kept constant contributions. But now I say constant contributions is not how most of retirement plans are organized. Most of these plans, they assume that your contributions grow in time to adjust for a few things, at least to adjust for inflation, right? But also maybe to adjust for, expectation for your future increase labor income, something like that. Your compensation will hopefully grow in time, and therefore you would be able to afford to contribute more. And therefore, I specifically restrict myself to considering two parametric family of policies, which has exactly two parameters, which I call here U naught and Xi. My policy, so this UT that I introduced before as a function of T is now specifically depends on T in this way. All right. So what this parameterization suggests is that if Xi is 0, right, then this means that UT is equal to U naught, which means that each month you will contribute the same amount, right? So U naught would be a constant amount if Xi was 0, but if Xi is not 0, then Xi will be essentially the growth rate of your monthly contributions, right? Okay, so my control is two-dimensional again, the two parameters. Why not? Sorry, U naught and Xi, right? So, okay, so having said that, it's convenient for me to introduce a new dimensionless variable, which I call V sub t here. And this V will be defined as essentially the ratio of my contribution, UT, divided by portfolio value, this thing. I additionally multiplied by this factor to make the whole thing dimensionless, just for convenience, but essentially what's critical here is this ratio, that my new variable, you see it's a little bit interesting, right? Because it blends together the state dependence, which is state variable is here. This guy is my action variable, and my new variable is the ratio between them, essentially, right? So if I now plug this previous expression in this formula, then I get another expression for this new variable. So this is my new variable, and I can rewrite my previous SD, which I had here, in terms of this new variable V, and my new dynamics will look like that. Right. So, and this equation has a name, turns out to have a name. If you So it's called, some people refer to this equation as stochastic Verhulst equation by the name of this gentleman who proposed it in 19th century without this term. So it was deterministic Verhulst equation for him, right? But it was proposed as a way to model population dynamics. So now what you can see here, what's interesting about this equation, right? You still see that the volatility term is still log linear, right? The same as geometric Brownian motion, but the drift term, you see it has the quadratic dependence on the state variable. It's proportional to v here, but also v here, right? So it's a quadratic function. Somehow, like what we did, we start with linear dynamics. A little magic already happens here for the first time. We had linear dynamics, which was controlled, right? It was not just linear dynamics, it was controlled linear dynamics. But everything was still linear here, right? At least in this at this stage, right? But here, when we did this transformation, all of a sudden we get non-linear drift, right? All right. The interesting thing is that this new equation does not depend anymore on one of our controls. It does not depend on U naught. U naught only appears now in the initial conditions for this variable, but not in the equation itself. The equation itself only carries the dependence on the second control, which is here, which is nice, kind of nice, all right? But that's not the whole story. Now I want to do another transformation to this equation, and I want to introduce another variable, which I call x, and this variable will be a minus log of the previous state variable v, which we called. And so we had this equation for v. Now we do this transformation, and we get the new equation in terms of new state variable x. This equation is shown here. All right. So okay, this part is pretty much standard. This log transformation is usually done in order to get rid of the state dependence in the diffusion term. You see here, diffusion term was linear in the state variable. Now, when we did this transformation, the diffusion term is normal, right? So it simplifies things, while the drift term becomes this function, all right, where I introduced the new combination of parameters, which I called here eta, and this eta is equal to this combination. So my previous expected return plus ethos correction plus this control. That was my control, right? So this rate of change of my contributions was the control, but now I can effectively treat this new parameter eta as my control. Anyway, so this is the control diffusion, right? And now what I'm saying is that now this equation we can view as a particular specification of a more general equation called Langevin equation. And Langevin equation is usually written in this form. So the difference between this equation and that equation is that you see, like this drift we wrote as a negative gradient of some function, which is called Langevin potential Vx, right? And so this is very general equation. You can apply it for many different choices of Langevin potential, but for our particular problem, if we compare this equation and that equation, we will see that our problem corresponds to a particular choice of this Langevin potential, which is shown here. It's a combination of linear function and exponential function, right? So now we have this equation. This is Langevin SDE. We can solve this equation for this potential under a particular initial condition, which we initially had, all right? So this completes the Langevin formulation, the path-based formulation. But what I want to do next is, instead of considering this path-based approach, to instead consider probabilistic approach, right? And this, we know how to do this. So instead of Langevin SDE equation, we can consider two partial differential equations. One of them is called Fokker-Planck equation, and this is the forward equation, which describes the probability density of your state variable, which we call f of x and t, at some future time t, given initial condition. Right, and in our case, it's also not just a Fokker-Planck equation; it's controlled Fokker-Planck equation because we still have controls, which we had, right? So, and these controls are embedded in two things: in the initial condition and also in this potential function. So it's controlled FP, right? And this forward-based equation. There is a second equation which is also very convenient, widely known in finance. It's called backward equation. So backward equation, it has like formally the same arguments as here, x and t, but the reason it's called backward is because it describes the future as seen from today, which means that this p is more specifically defined as the conditional probability of the terminal value of your state variable to be below some threshold, which we call here x hat, conditional on the current value of x equal xt equal to x, right? So these variables are backward variables, these variables are forward variables referring to the future. All right, but the equations themselves, they look like very similar to each other, right? So both of them are second order PDEs, right? But the difference is that this equation is solved under initial condition, which is stated here. The other equation should be solved under a terminal condition. We know this from, Finance 101, Black-Scholes theory, etc., right? Black-Scholes equation is a version of this equation, as some of you, all of you might know. All right, so for this equation, because we define this P, I define this P as the tail probability, right, for the state variable to be below some threshold, and therefore you can figure out the corresponding terminal condition for this equation. It has this dependence on a step function. All right. So we're getting closer to the punchline in this equation. So now I have in principle, I don't have to work with both equations. I can choose to work with one of them. And initially in the paper, I tried one. I saw some technical challenges. I can talk in more details later what they were, these challenges. Which made me think that maybe backward equation would be more numerically efficient. So at the end, I looked at both, and I found that they have about the same level of complexity. And on some count, it's better to analyze them simultaneously, which I do here. And it turns out that it has some merits, all right? So we have these two equations. One of them Fokker-Planck equation, and the other one is backward equation. The forward probability is denoted as F. The backward probability I denote here as P. All right. So what I do, first I start with change of dependent variable, and instead of these functions F and P, I introduce new functions which I call psi and psi bar, and they are related to these unknowns in this way. So exponential adjustment, exponential correction in both cases, right? But with different sign. That's one difference between these two formulas. And there is another difference. I want to make a transformation such that my new equations for new quantities psi and psi bar would be both forward equations. The previously we had this equation was backward equation. And therefore, I have also changed the time variable in this equation. You see that I have some tau here, and this tau is the backward time. Tau in the second equation, I have this tau, which is defined as difference of capital T minus T, which means that if I had if I had the terminal condition for this guy, it would translate into initial condition for this guy, which is what I want. All right. So I do this transformation. This one is very standard. This one is not standard, but still simple and looks very similar. So if I do this transformation, then my previous two equations translate into new equations, which I call here a controlled Schrodinger equation. So for those of you who do not know anything about quantum mechanics, there is nothing that you should know specifically about quantum mechanics at this stage. It's only the fact that this PD has a particular form. It's a second order differential operator, which you have here. And that's the only thing why, that's the only reason why it's called Schrödinger equation, right? And it's actually not quite a Schrödinger equation in the conventional sense of quantum mechanics for another reason, which is the thing that standard quantum mechanics has imaginary unit here in the time dependence, and here we don't have this. So this equation is a real valued equation. We don't need any complex valued functions or whatever for these equations, right? Some people refer to this as Euclidean quantum mechanics, if you wish, physicists, right? But both these equations, so I got two equations. One is obtained from the Fokker-Planck equation, and I call it FPE Schrödinger equation, which is this equation. And another equation is what I call the backward Kolmogorov equation / Schrödinger equation, which is this one. So both equations look the same, right? That's the nice part, right? But obviously, they still have different initial conditions, right? Because initial conditions for these are inherited from the previous initial conditions. So equations are the same, but solutions will be different because initial conditions are different. Nevertheless, the mathematical structure in both equations is the same. The operator that stands here is the same for both equations. And therefore, for example, we can use like the same methods to solve these equations. Solutions will be different, but methods will be the same.
So Igor, I had a slight worry that we would have an imaginary number and then no one wants to retire with some imaginary money, right? We want
no, there's no imaginary numbers. There is no Schrödinger cat in this formula. There might be some interesting. That's actually like it's like I don't want to drive in this direction, but you kind of hinted at a very super interesting question, like if there is no imaginary unit here, what of the actual quantum mechanics remains? Is it like just the PDEs? So for me, like here, it's just PDEs. So we can forget everything that we know about quantum mechanics. You would not lose almost anything because I'll give you the solution, right? And the only thing that I actually use here is the way to solve this equation using pretty standard tool. So I'll get back to this. So like the only thing that I actually use from physics is the way to find some convenient basis to solve this PDE using what is called eigen value decomposition. Very, very standard things, nothing fancy. So no risk for you to for your wealth to become purely imaginary. Right. Yes, but okay, but it's still like very fascinating to see like what do we have, any quantum effects in this version of quantum mechanics. It's an open question for me. Anyway, what I wanted to say is that this is so far it's just the mathematical transformations, right? So I just transformed two equations, right? We know from standard math finance courses about what is called Feynman-Cass theorem, right? Which relates solutions of the backward and forward equations in a conventional, formulated in conventional terms. Now, because I reformulated them, both of them in terms of these new functions, psi and psi bar, I can find equivalent relation to Feynman-Cass formula, which is shown here in terms of my new functions. So all this is just mathematical, convenience. What is interesting, nevertheless, is that when I look at my potential, like I told you that my potential actually was, so I have two potentials I have to mention, right? So first I had this potential which I called V, right, which was the potential in the Langevin equation here. Here, right? I call it V, and this V was the combination of a linear function and exponential function. Now, when I do this transformation to Schrödinger equation, I get a new potential, which is now called Schrödinger potential, which appears here. And the Schrödinger potential is related to my previous Langevin potential by this formula. And this formula is highly non-trivial, actually, and very how to say it, universal, right? So people actually did discover it. I'll show you shortly who discovered it and why it's important. But look at the structure of this expression, right? So it's non-linear because you take the derivative of your potential and you square it, right? So it's some other function, short, right? So the interesting part is that if I have this function v here, and then I do this calculation, I recompute my Schrödinger potential, which I call u, as I just explained, it will have this form, all right, with some parameters which are defined here in terms of the original model parameters. You can see, like, we can, there are a few things interesting here. First, we track the dependence of this potential on our controls. And our control was here in this parameter psi. And then you can see that actually all parameters in this potential, which is this d naught, depend on my control. Actually, I have to start here. So this parameter g is defined in this form, and you see that it depends on control eta or on the original control psi, right? And now this parameter d naught depends on this g, and therefore it also depends on the control, and also the constant term. So in short, it means that now I have the Schrödinger equation where my potential is controlled by me, which is important, right? That's the difference from, physics. In physics, you cannot control the potential. You can control something related. Here, we directly control non-linearity of this potential, right? Our contribution is what controls it. That's observation number one. Observation number two is that actually this potential is actually very, very famous potential. And it was discovered first by this gentleman named Morse, and it's called Morse potential. I can rewrite it in this way. It's the reason it's very popular is because it's very tractable, and that's why quantum physicists love this potential and apply it whenever they can for molecular dynamics, right? So here, it's funny thing is that we started with very conventional, financial mathematics, and somehow came up with this potential, which is nice. All right, now I think maybe I can skip these more technical parts, but like what they show is that what I try to show here, maybe it would be a little bit too specialized. Essentially, there are beautiful methods in physics which suggest a way to solve Fokker-Planck equation by reducing it to this quantum mechanics, which turns out to be not just a quantum mechanics, but rather a very special kind of quantum mechanics called supersymmetric quantum mechanics, which was proposed by this guy who's considered the greatest theoretical physicist alive. His name is Ed Witten. He's currently at Institute of Advanced Studies, and supersymmetric quantum mechanics was suggested by him in 1981. And then literally 1 year later, these two gentlemen, they established a link between classical Langevin dynamics and this supersymmetric quantum mechanics by Witten. So what they essentially showed is that Langevin dynamics is mathematically equivalent to supersymmetric quantum mechanics of Witten. And why it's useful? It's useful because it allows you to apply very powerful mathematical approaches to solve dynamics in such systems. It turns out that you see, I alluded here, where was it? Yeah, for example, here I alluded to a very particular form of this potential. I told you that the Schrödinger potential has a very special form for this problem. It has a square of the derivative plus the second derivative, essentially. And because of that, it turns out that for this particular class of problems, the Hamiltonians can be factorized. So instead of second order differential operator, which was the initial Hamiltonian, actually it's one of them. Let me skip the reason why the second one is important. But the thing is that your differential operator can be factorized into a product of two first order differential operators, which are shown here, where this calligraphic Latin W is the gradient of the potential, of the Langevin potential. And it turns out that if you have this decomposition, then the problem of finding the lowest level state of this system can be reduced to solving a simple first order differential equation. This is why this approach is, that's part of the reasons why these approaches are useful for this particular problem. I'll probably skip the details, but the thing is that the reason I mention all these links is that is the fact that supersymmetry allows us for this particular problem to find a very convenient basis for decomposition of the differential operator in our equation. And this basis is based on the supersymmetry. I'll probably skip all this in the interest of time, the way this orthogonal basis is formulated. But once you have this basis, basically we can reconnect, maybe not here, but yeah, here. So you can just take my word for this, that physics-based approach allow you to come up with some very convenient orthogonal basis. And you can now, once you have this good orthogonal basis, you can expand all your unknown functions in terms of this basis. And one of these expansions for the forward equation, which was the equation for function psi, is shown here. So this is just, very standard things, right? So forget about what particular expression you had here. As long as you have orthogonal basis, then you can expand any function in terms of this basis and then find the coefficients. And that's actually how we solve both problems here, right? And so we solve them. So we can solve the forward problem, we can solve the backward problem. I mentioned to you that initially I thought that they would have different computational complexity. It turns out not to be the case. They are more or less equivalent in terms of compute time, etc. Right. What I also found is that, unfortunately, parameters, which are realistic parameters for the financial problem in this setting, are such that convergence of this expansion is very slow. And this is as expected. Actually, all expansions that we get in this approach are they produce what is called asymptotic series. An asymptotic series, if you're familiar with the theory of these guys, they do not converge. They're only as good as, when you get close to the point at which you make an expansion. They do not converge in terms of, collecting more and more terms. And this is what we saw here. So I did have in reality, this is Sasha to your question. I don't have a risk that my wealth will become imaginary, but I do have risk that I would not be able to measure it very accurately. Okay, so I had some indications that, like, maybe something could be done even at this stage of improving numerical approach here. And there are various ways which I illustrated in more details in the paper how I diagnose this. But nevertheless, when I like the punchline is here, we have, I think, 10 minutes or so. So I think it would be enough. The punchline is shown here. So using this eigenvalue decomposition, using all this heavy machinery, I can come up with the basis. I can expand all my functions in this basis, and then finally produce a solution, two solutions actually, to both of my problems. For the forward problem, which was based on the Fokker-Planck equation, and also for the backward problem, which was based on the backward Kolmogorov equation. So here I show only the second part, only the solution. So you see two profiles here. One shows you the solution of the Schrödinger equation, which I obtained, and it's shown in terms of two of my controls, right? Remember, I had two controls. Actually, it's not quite that. So one of these variables is my original control psi. The other variable here, something that I did not show here, the other variable here is actually a variable which is, for historical reason, it's called Morse variable. It's related to my x in this way. What you can see here is that essentially you can treat it as a rescaled first control, U naught. And that's the way to think of these profiles. So basically, again, the variables here are my controls. This variable is my rescaled first control variable. This variable is my original second control variable. And these are profiles, right? So you see, like, it's like a profile of a mountain, right? If you wish, right? In these coordinates. So this is what we get on the left, what we get for function psi bar. And on the right, what we get for the corresponding backward Kolmogorov equation density, which we call P. So once we get this, right? And they look kind of similar, right? So something similar. All right. Now, finally the most interesting part, how it all relates to the problem of goal-based wealth management, and what is the problem that we solve. So you see, like here, I showed you the complete solution. So basically, this graph gives you all solutions for any controls. What we're actually solving, the problem that we're solving in this approach is shown here. So we want to find such values of control, y naught and psi, such that this thing, which is the tail probability, this is the probability that my terminal wealth expressed in terms of this other variable, which I call Morse variable y, it's basically terminal, will be above some threshold. And we want to find control such that this probability is equal to my target confidence probability level, alpha. Industry standard is alpha equal to 5%, right? Now, if you think and conceptualize this equation, you will see that this is not optimization problem, which is the critical observation here, right? This is not optimization problem. This is rather a problem of finding lines of a constant level on this surface, right? And now I just flip, actually these lines are like, I flip this surface here to show exactly these lines. So these lines are constant level lines corresponding to different values of alpha, right? But any point on this line, so if we take one of these lines corresponding to this industry standard value is this 5%. So if I define that my alpha equals to 5%, right? Then what I see from my solution gives me all solutions. Like my representation of the solution of the backward equation gives me all solutions to my original problem. And what I see from this graph, this is just the flattened out this graph, right? What I see from this graph is that any point on this line is as good in terms of my original requirements as any other point. Any optimization-based approach will not give you these continuous lines, all right? It will give you a point because it will be based. That's the difference, right? So that for me, it was kind of interesting observation because I never saw it discussed anywhere in the literature. When we do optimization, we target a peak of a mountain in this decision space. So optimization would correspond to reaching something like this point here, right? But that's not our problem. Our problem is simply to find good enough solutions which correspond to particular level on this surface, right? So that's why like levels will be lines here, and these lines are shown here on the three-dimensional surface and also shown here on two-dimensional surface. Now you see that these lines are a little bit non-parallel, and I think that's the measure of like how much accuracy I lose because of my truncation of series. So they still do not cross, which tells me that it's more or less okay, but I think my estimation may have like slightly, maybe slightly inaccurate because of specific things that I do by truncating infinite series, right? Now, a little maybe controversially, I called in the paper these contour lines, I call them efficient frontiers in a similar sense to Markovit's portfolio theory, even though his efficient frontiers were something different, right? So I call them efficient frontiers in the sense that like any point on this line for any chosen value of alpha is a good solution, right? So that's the statement. That's the interesting observation. And finally, what it does bring to comparison here is rather what's striking here is rather its similarity of this solution to this celebrated satisficing decision-making theory, which won Nobel Prize in '79 to Herbert Simon. And according to Simon, his approach to decision-making is not based on optimization. It's based on combination of two steps, which he called search and satisficing. And what is satisficing? Satisficing to him means optimizing just enough, but no more. That's exactly what we do here. We're satisficing just enough and no more. And that's why we end up with the continuous lines. So my interpretation of this approach is that somehow goal-based wealth management in this formulation actually is a particular case of the satisficing decision making theory of Herbert Simon. All right, so yes, now so and now this brings to me at least all sorts of questions about what we actually do in other approaches. Like here, I was lucky in a sense because I used a different approach. I did not use standard methods of Hamilton-Jacobi-Bellman equation. I did not reduce it to optimization. I found all the solutions which exactly correspond to original formulation of the financial problem. Nevertheless, a big open question would be, okay, how, like, if we don't have this analytically tractable formulation as I had now, what if we use something like, deep reinforcement learning, right, which is essentially a black box approach? Like, how would we find these continuous families of solutions which I identified here in these purely numerical settings? I have no idea how to do it. Right, so that's one observation. The other observation is what I already mentioned, is that this whole analysis seems to suggest that we don't need adaptive control, setting of adaptive control in most of problems of this sort. Approaches based on model predictive control, which is exactly what I use here. We set the policy and then we follow it. In my setting, we assume to follow it till the end. In practice, it can be revisited in times. So overall conclusion is that RL, like my new understanding based on that, is that RL may be not a good approach for goal-based wealth management. And also it's as I said, it's a big open question how, like, if for more complex problems with multiple goals with a different reward function, where we would not be able to use this simple analytical approaches, how we would find continuous families of solutions. Right. Very finally, I also wanted to mention, which is something which is maybe a little bit more controversial point, is that given that I solved my problem by reducing it to Schrödinger equation, actually not just Schrödinger equations, but to control Schrödinger equations, as I mentioned, my setting is that when I have this control. So essentially, mathematically, at least, my problem reduced to what is called quantum optimal control. And this brings other interesting questions. For example, can we use quantum computing to do calculations of this sort? I don't know yet whether, I mean, we certainly can do something. And there is a paper which is referenced here, which I found when I tried to do search whether people tried anything of this sort. It turns out that yes, it's a recent paper where people, as a proof of concept, they use quantum computing, IBM quantum computer, to compute a few lowest eigenstates for this very potential, for the Morse potential. My problem goes beyond. I don't need just a couple of eigenstates, I need all of them, right? But more interesting question is, like, obviously, literally using quantum computing for this one-dimensional problem would be a complete overkill, but for possible extensions of this approach, it might be interesting solution. So my summary is shown here, and it says that goal-based wealth management equals satisficing decision making. Now, satisficing decision making is not equal to optimization. Goal-based wealth management is not equal to reinforcement learning, but it's rather equal to quantum control. Right, and maybe a couple of the very last comment, as I already mentioned, like, even in this simple one-dimensional setting, where everything is semi-analytically tractable, nevertheless, to compute it, you still have to operate with, infinite series, which you have to truncate, etc. And it might be that, there might be other approaches to solve exactly the same dynamics, maybe not based on reducing it to Schrödinger equation, but, for example, using new types of integral transforms, which were presented in this paper by my friends and colleagues. And that's more or less it, what I wanted to present. Thank you very much. If there are any questions, I can answer.
Okay, Igor, well, thank you so much for this very deep talk that I think has a lot more equations than any talk we've had before, but therefore maybe it requires a second viewing, but that's, I guess, why we're putting it on YouTube, and hopefully I will also be able to digest a few things. So, we don't have any extra questions. So maybe one last one sort of for the road.
I see one question from
Yeah,
Olga.
we've got a raised hand, but maybe if you could type in the question, I'll read it after my question.
Yes, I see the
But
good news is that participants, I don't see that many people ran away when I
yeah, they're meditating on these equations, and
That's what I suggest. Never try to understand completely. I understood early on that it's not feasible, right? So it's always okay when you miss something.
So the part that I'm curious maybe to hear your interpretation is that we sort of started with a control problem with one control, which is, every time you contribute, how much do you put in the stock and how much you put in the bond, and then after a lot of transformations, you did end up with two controls. So
No, it's actually no. It was two controls from the start. The control, you see, like so I differentiated between, like, remember I said that from the point of view of retiree, I'm not concerned with the rebalancing part, right? I leave it to the fiduciary to maintain. So my problem is how much to contribute. But this thing has 2 degrees of freedom, right? One is like, if I contributed equal amount, that would give me one parameter, which I called U naught, U0.
Mhm.
But I also had another parameter which I provisioned for any possible changes of the first parameter. So my control was two-dimensional.
I see. So if at the end you end up with these level sets, so that means that your decision is related to the
These are exactly this.
advisor's decision. Yeah.
Uh,
Or is that a way I should interpret these two controls? Is that one of them is yours and one of them is the
no,
fiduciary?
no, both are mine. Both are mine controls.
Okay.
Because this is what I like. I can tell you, like, usually, like, for this, for example. So as I said, this Y is just, you can think of this as a rescaled initial wealth of your portfolio, right? It's just my convenience. This parameter is the rate of change of your contributions. Usually, by talking to colleagues in industry, they explain to me that the typical range is around here, is about between 3 and 4%.
Mm.
All right, and this 3 and 4% actually related to the expected level of inflation. All right. So short of if like, and this is more or less like default setting in most of these plans, right? So if you employee, right, and you currently 25 or 30, right? So you have 25 or 30 years or something like that of active working in the industry, right? So you're planning for a long time horizon, right? You can add something on top of this 3 to 4% in order to incorporate your future, expected increase in your salary, right? But that would be on top of these like minimal assumptions, right? Because and this is like adjustment for inflation is routinely done in these plans, and that's the way to incorporate it. So it almost doesn't make sense, and that's why I showed this range here, because actually it never goes beyond this range in either direction. It's never essentially like no one looks at the plans where this psi would be zero, which would be like in this thing. Do you see what I'm saying?
Okay. And so I guess we got the final question in the Q&A, and it's now another one. All right.
Huh?
So first of all, is there a code that shows did you share any of this code online, or is there somewhere where someone who wants to implement this would be able to find help with the paper?
Uh, I didn't share this online.
Okay.
It's the code is pretty straightforward. I mean, like there is literally it's a few hundred lines, so maybe
Okay.
2,000 lines of Python. It's nothing
Okay,
fancy.
well, we'll leave it as an exercise then.
Yes, yeah,
Um,
it's a good exercise.
and it's part B of that same question. What would be the difference if volatility changes over time? So I guess the retirement with stochastic volatility problem, is that something you imagine being doable, or do you think it's a level of complication? Uh,
Uh, uh, Frankly, I think that would be unnecessary level of complexity for this type of problems, right? Because as I said, the games around changes of volatility is, I wouldn't call it second order effect, because like when you say second or first order, you already like kind of pretend to mean more than you say, right?
mhm,
But I would say that normally like people go with pretty simplistic assumptions about changes of volatility, or you see, like I didn't even assume like something like changes of regimes or things like that, right? So for these longer time horizons, like you probably more or less okay with assuming the simplest assumptions about the volatility. What is certainly more interesting, and that's what I meant as a continuation of this work. But today, I don't know if Agostino made it to the audience. He said that he planned, but he just sent me a recent paper of him, where he already addressed multi-go formulation, which I meant to be the next stage here. So now it gives me homework before I go to multi-go formulation. I have to check exactly what he did in his paper, right? But that was the plan. Like more interesting practical questions are rather in this direction, right? How you have something like operational, something that you can quickly run, but also explain to your clients in the realms of multi-goal planning, right? Yeah.
Okay, Igor. Well, thanks again for really a great talk, and we'll post it on YouTube and see how viral it goes.
Nice session. Thank you
All
for
right. Have a good evening. Bye bye, everybody.